We've got a ball is thrown into the air with the velocity of 40 feet per second. Its height in feet after t seconds is given by this function right here. This would be the position function. You want to find the average velocity for the time period beginning when t equals 2 and ending and lasting a half a second. So what would be the ending time? 2.5. So it begins at 2 seconds and ends at 2.5 seconds. And I would like to find the average velocity. So how do I find the average velocity? Okay, so change in position, same as the change in distance. You might like it better if I call it the change in position. Change in position over change in time. So how am I going to find the change in position? That's the one you really have to think about. Do we have a function to represent position? What is the function that represents position? 40t minus 16t squared. And the t in this position function is what? T stands for turtles. Is that what the t is for? No, it's time. Okay, t is time. So the change in position means you have to take into account your two times and find the difference between them. Remember in the previous example for average velocity, the change in position is the position at the end time minus the position at the beginning time. That's the change in position over change in time. Okay, so how do I find the position at the ending time? What is the ending time? 2.5. Where would I put 2.5 to find the position at the ending time? Wouldn't you put it in there? Isn't that the position at a given time? So the position at 2.5 seconds, I would take and put 2.5 into that position function. So if we called the position function s of t instead of y, we'd be finding s of 2.5 minus s of, what's the beginning time? 2. And what amount of time has passed? What's the change in time? 0.5. A half a second has gone by between 2 seconds and 2.5 seconds. So how do I find s of 2.5? I just plug 2.5 in there. So I'll have 40 times 2.5 minus 16 times 2.5 squared. From that, I'm going to subtract what I get when I put 2 into that function. Notice I put the parentheses. I'm subtracting the whole thing. So 40 times 2 minus 16 times 2 squared, all over 0.5. So this is where I just get my calculator out and type it in exactly as I see it. 40 times 2.5 minus 16 times 2.5 squared minus begin parentheses, 40 times 2 is 80, minus 16 times 2 squared is 64. And I get that the average velocity is 81.44 what? What would be the label on it? Cars. Cars, is that the label? Inches per mile? Feet per second. Oh, you know what I didn't do? What do I have to divide by? That's over 0.5 still. So the average velocity is that divided by 0.5. So that's 162.88 or 0.9. And the label on velocity? Feet per second. I think I typed that in right.
I got 32.
Oh, you did? Okay, well, let's see. What did I do wrong? 40 times 2.5. Oh, yep. You know what? I hit the divide instead of the times button. So minus 16 times 2.5 squared minus 80 minus 64. Okay, that should not be 81.44. That should be negative 16.
Yeah.
Okay. Right here, when I was punching it in, I hit the divide instead of times button. So negative 16. So the average velocity is equal to negative 16 divided by 0.5, or negative 32 feet per second. Okay, in your homework, you've got 3 average rate of change. Average velocity is also known as the average rate of change. I guess that's just the way they refer to it. Average rate of change. Average velocity, that's how they refer to it. And instantaneous, okay, so what would be the instantaneous velocity at 2 seconds and 2.5 seconds? So just going with the same function, the same position function, S of t is 40t minus 16t squared. What would be the instantaneous velocity at 2 and 2.5 seconds? Yes, what did I tell you the instantaneous velocity is? The formula is derivative. Instantaneous velocity, v of t, is equal to the derivative of position. So what is the derivative of position? 40 minus 32t. The derivative of 40t is 40. The derivative of negative 16t squared, you multiply by 2 to give you negative 32. Subtract 1 from the power to just give you t.
So you're going to do v of 2 minus v of 0.5?
No, you don't need to do minus. You're just finding 2 different velocities at so this is 2 separate answers. The instantaneous velocity at 2 is v of 2, which is 40 minus 32 times 2. What's that? 40 minus 64, negative 24 feet per second. And v of 2.5 would be 40 minus 32 times 2.5. What's that? Negative 40 feet per second. So at the instant, it's at 2 seconds exactly, it's going negative 24 feet per second. At 2.5 seconds, it's going faster. Does that make sense? Mm-hmm. If it's a free-falling object, what's it doing as it goes from top to bottom? It's getting faster. So does it make sense that the instantaneous velocity over that half second increases? Okay. There's a difference between an average velocity over that time and instantaneous velocities at specific times. So your first homework, well, not your first ones, all the stuff that I'm doing now is basically 90 through 96. The part that says 90 through 96, 98, and 100, which we're just now going to go over how to do 98 and 100 and 100. So you don't have a ton of these on your homework, but they'll come up periodically in other homework assignments too. Little physics applications of calculus. So you could have a whole calculus-based physics is what you can take. So you can use derivatives and second derivatives, which we'll learn about soon, to do physics. All right, so the last example that I want to look at is just this number 8 right here. It's not a trapezoid. Okay, just number 8. It says the graph in figure, well, this is the picture. That graph represents the distance in feet covered by a moving particle in t seconds. And then it says, draw a sketch of the corresponding velocity function. All right, so what I want to do, this is the position function. It's labeled S of t. You can't really see that. Position. So I am going to make its corresponding velocity function by making a graph very similar. I'm going to label it and try to put the marks in the very same spot. Okay. Now, this is the graph of the velocity function, v of t. So the bottom is still time. Okay, so the bottom is still time, but this is the velocity. This is the speed. Okay? So how is velocity related to position? It's the what? It's the slope. Isn't it the derivative? Isn't velocity equal to the derivative of position? Isn't derivative the slope? So basically, here's how easy it is to draw the graph of velocity. If I remember, velocity is the derivative or slope of position. If this is my position, basically over a second, a position is the distance. So if I think of this maybe as distance in feet or in feet. So after 1 second, how many feet have I covered? 2 seconds. After 1 second, I've covered 2 feet. Okay? So the slope of this line is rise 2, run 1. So the slope of that, the derivative of that is 2. So over the first second, what would the graph of velocity be like? It would be at 2. It would be just a line at 2 right there. Because isn't the slope of this 2 the whole time? Okay. So then, isn't this another segment that we're doing the same thing in our position? What are we doing? From 1 second to 3 seconds, how much distance did we go? Nowhere. We stayed at 2 feet away. So it's like you were at a stop sign. No, you could think of this as miles too. You could say, over the first minute, I drove 2 miles. That's kind of going really fast. That's, okay. Over the first minute, I went 2 miles, and then the next 2 minutes, I just sat at a stop sign. Or I sat because I got pulled over by a police officer. Okay? So what is your velocity over that time? What's the slope of that line? 0. So from 1 second to 3 seconds, you're going to draw a line down here. You don't connect them. They're 2 separate lines. So this, you don't draw a straight line down. No, you don't. That is not part of a graph. Okay? This is called a step function. Okay? Now here, from 3 seconds to 5 seconds, I must have gone back the other direction, right? The slope is negative. Okay, over 2 seconds, I drove back. But how fast was I going? What was my slope? Down 2, forward 2. So what was my slope? Slope was negative 2 over 2, which is equal to negative 1, right? So then the velocity function would be a line at negative 1 from there to there. Velocity is the derivative of position.